So, hello class. Today we will integrate the differential rate equation of the rate law expression, and the topic will be integrated rate equation. For that, we will actually find out how the given rate equation and the value of zero order or the first order can be integrated, and to get the different integrated rate equations. Today lecture will based on the integrated rate equation for the zero order reactions. First we will try to integrate the zero order reaction, then for the first order reaction, and we'll try to learn the graph and half-life period for the same. Okay, so let's discuss about the zero order reaction integrated rate equations. Integrated rate equations, huh? If I will take a general reaction for the zero order. So the general reaction will be like this: R gives out P. A general reaction is R gives out P, and you can write like rate equal to K R to the power 0. This indicating the rate of the equation is independent of the concentration of the reactants. So this will be the R to the power 0, indicating the zero order reaction. You can write like this: minus dr by dt equal to K, and R to the power 0, that will be value 1. R to the power 0 will give you a value of 1. So on rearranging this formula, this equation, you can write like this: dr equal to minus k dt. dr equal to minus k dt. This is a simple differential rate form, rate expressions for the zero order reaction. Now we will try to get the integrated value of this given equation first. Okay, on integration both sides, this formula, this equation first will become R equal to minus k t plus I, minus kt plus I, equation number second, where this I is integrated constant, and you can see on integration this dt become t and this dr become r. Okay, so this is the integrated form of the equation number first. Now we will try to calculate the value of integration constant I. Okay, for that, suppose at time t, in the initial condition, when the reaction begin, the time equal to 0. For that condition, the initial concentration can be write like R naught. This is called the initial concentration. At the time T0 means the reaction going to begin. So the concentration called initial concentration, and these two value, if we'll put in the equation number second, we will get from equation second, we will get R naught equal to t equal to 0. This will produce 0 and plus I. So I equal to the integrated constant value will be R naught. So I equal to R naught at the time begin 0, at the time reaction begin, time equal to 0, and this value of I, when we will put into the equation number second, then we will get equation second becomes R equal to minus kt plus R equal to minus kt plus R naught. This is called equation number third. This is the integrated rate equations. Integrated rate equation for the zero order reaction. And you can just rearrange to get the value of k. The rate constant value can be calculated with this equation by rearranging. So rearrange this equation. Minus kt will come this side, will become plus kt, and R will go that side to become a minus. Okay. So this can be written like this: kt equal to R naught minus R, or you can write like K equal to equation number fourth. Equation number fourth. This is not visible, I think. Equation number fourth cannot be visible, okay? So we can rearrange it in the above side. Equation number fourth. On rearranging, this will become K equal to R naught minus R upon T. Okay. So with the help of equation number fourth, we can calculate the value of rate constant with the help of initial concentration, final concentration, and time given. So these four equations, you can see that the first equation called differential rate equation, and on integration we just get the value of integrated rate equations, and you can see the different value. On putting the rate constant value, we have the equation number third, that is called integrated rate equations. And on rearranging, you can calculate the value of rate constant with the help of integrated rate equation for zero order reaction. So for zero order reaction, the K will be just difference R naught minus R upon T. With the help of this equation, you can calculate the value of rate constant for any given zero order reaction. Now we have to be trying to solve the graph. How to draw the graph? For that we will use the equation number third. Equation number third must be compared with y equal to mx plus c to draw a y and x graph. For this purpose, we will just compare r equal to minus kt plus r naught with y equal to mx plus c. You can see on comparing, this will become y. This is called mx and this is called c. C means constant, M means slope, x-axis, y will become y-axis. So you can see, if we will just draw the graph R versus T, this graph will look like R versus T graph. The graph will be look like there will be a constant value. Constant value means here for the graph the intercept is a constant. Intercept, when the slope touch with x-axis either or y-axis, it is called intercept, and that will be called a constant. Here R naught is the initial value, that is remain constant always, and minus k indicating the value of slope, the minus sign indicating the slope will come downward. So this will look like this. The graph look like this. The slope is coming downward, indicating minus k. Slope equal to minus k, and this is called intercept. This is called intercept. This must be equal to the constant value r naught, initial constant. So when we draw the graph, the final concentration versus time, we can see that the slope always indicating the value of minus k, the rate constant value, and the intercept indicating the initial concentration of the reactants. So this is the overall integrated rate equation and the graph study. Now we have one more point, how to calculate the half-life for zero order reaction. Half-life means the half-life indicating in which time the concentration, the initial concentration become half of the value. The initial concentration become half of the value. That time duration is called half-life period. The time duration called half-life period. For that, we just indicate the time t with t half, and the concentration, the final concentration become the half of the initial concentration. For that, let's discuss the value, the equation. I am calculating the half-life for the zero order reaction. T indicated by T half, and final concentration must be the half of the initial concentration. So the time duration in which the initial concentration become half of the value is called a half-life period. Okay, for a zero order reaction. So these two values, when we will put in the integrated rate equation number 3rd, what we will get, or you can put the same value in the rearranged value, that is equation number 4th. You can put this value r and t in any one of the equation. So I am going to put in the equation number 4th. From equation number 4th, the formula is k equal to r naught minus r, and instead of r we have to be write r naught by 2 upon t half. On rearranging, the formula will become t half equal to 2 r naught. This will give you 2 r naught minus r naught, that will produce you r naught by 2 and k. T. So half-life formula for the zero order reaction is equal to T half equal to R naught by 2K, where R naught is the initial concentration and K is a rate constant value. So students, you can see that the half-life for the zero order reaction is depend upon the initial concentration value. Half-life depend upon the initial concentration value, but rate constant, rate equation, the rate of the reaction is independent of the concentration. But half-life depend upon the initial concentration as well as the rate constant. So with the help of this equation, equation number 5th, you can write like equation number 5th. You can calculate the half-life for a zero order reaction. At the same time, you can also draw the graph. You can also draw the graph for that equation. For that equation, can you suggest what will be the value? Can you suggest what will be the value for the graph? Anyone? I am giving you a homework. Just draw the graph for the half-life. Okay? You have to be just draw the graph T half versus initial concentration. Okay? So try it in your homework copies, how to draw the graph for the half-life period in the zero order reaction. Okay? This is the complete topic for the zero order reaction. Now about some examples. Generally students, the initial concentration and final concentration and whatever the value given here, you should learn first thing, all those reactions in which the rate of the reaction is independent of the concentration of the reactants is called zero order reaction. So which type of reaction should not be, the rate of reaction should not be depend upon the concentration of the reactants? The answer is many of the reactions which take part at the upper surface of the catalyst. Upper surface of the catalyst is generally independent of the concentration of the reactants. Means all those reactions in which adsorption process takes place and reactants combine to form a product on the surface of the catalyst, generally they are a zero order reaction. For that, in your NCERT book, some of the example I think given. For example, the decomposition of gaseous ammonia on a hot platinum surface is a zero order reaction at high pressure. At the same time, the thermal decomposition of hydrogen iodide on a gold surface is also example of zero order reaction. These two examples given in your syllabus, generally the many of the reaction takes place on the surface of catalyst follow zero order reaction, because the decomposition or association on the surface of catalyst is independent of the concentration of the reactants, because that process actually depend upon the nature of the catalyst and bonding of the catalyst. It will independent of the concentration value. That's why they are called a zero order reaction. The same way we can integrate the equation of the first order. But before that, there is one question given in the text, question number 4.3 and 4.4. We can solve that question. Okay. You can note this thing from your board. Students, we will try to solve some in-text question given 4.3, 4.4. The question is, for a reaction A plus B product, the rate lies given. What is the order of the reaction? Question number 4.3. Product. The rate lies given like this: R K A to the power half B square. What is the order of reaction? So you are knowing that the order of reaction is the sum of the exponents in the rate law expression. This is the rate law expression. So the exponents given half and 2 must be summed up to give a total or overall order of reaction. But at the same time, you can say that the rate of the reaction is the proportional to A to the power half, and the rate of reaction for this given type of reaction is a square of the concentration of B. Okay, so in that with rate of reaction with respect to A is a half order, and rate of reaction with respect to B is a second order, but the total order of reaction is 1 plus 2 plus 2, and you will sum up this value, so this will become 5 plus 2. So order of reaction, overall order of reaction is 5 by 2. Okay. The next question is, and this question was actually many times asked in the board examination. So that's why it is important also. The conversion of molecules X to Y follows second order kinetics. If concentration of X is increased to 3 times, how will it affect the rate of formation of Y? In text 4.4, X converging to Y follow the second order kinetics. Second order kinetics means rate equal to kx square. This is called second order kinetics, means second order reaction. If the concentration of x is increased to 3 times, means the x become 3 into x naught. The initial concentration just increased by 3 times. So what will be the, how it will affect, the rate of formation of y? So you can see that the rate become 3 into x. The class, you can see that, okay, the thing is not visible, I think, okay. See, the rate become the 9 times because there is second order kinetics. So when the concentration is increased by 3 times, the rate must be the increased by 9 times. So rate of formation of y will become a 9 times of the initial concentration, initial condition. This is the equation, this is the question given by the asked by the board examination many times, and it is one of the simplest question I think we have. Okay, so you have to be go through the sum of the question given in the static exercise also, and we will discuss the first order reaction and some numericals based on first order and pseudo order. That will be the last topic of this chapter because the other topics are deleted. So for the board purpose, that will be the last topic: first order integrated rate equation, pseudo order rate equation, and the numerical based on the first order reaction. That will be the last topic. Okay, so we can discuss this is in the next lecture. Before that, we can discuss some doubts.